In Chapter 8, we used inference to take some sample data or a sample statistic like the sample proportion or sample mean and try and estimate a really good interval that the population version, so the population parameter, might lie between. So in Chapter 9, we're still working on inference, but instead of making estimates, what we're going to do is we're going to take a claim and use probability to assume whether or not that claim is true or false. So we kind of have to think a little bit like courtroom lawyers or courtroom jurors and look for convincing evidence. And our evidence lies in probabilities. So we say, according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to the study, the majority of couples tilt their heads to the right when kissing. And in the study, a researcher observed 124 couples kissing in various public places and found that 83 out of 124, or p-hat of 0.669 of the couples tilted to the right when kissing. Is this convincing evidence that the true proportion p of all couples that kiss the right way is greater than 0.5? Okay, so we're looking for evidence. Okay, we're asking ourselves, is this convincing evidence that the true proportion of people who kiss the right way is greater than 0.5? This is our evidence, and we have to decide whether or not it's convincing. Well, there are always two explanations for our evidence, our statistic. One explanation is that our statistic really does reflect the population, and that the true parameter, the true proportion, is greater than 0.5. Okay, that's one, that it is an accurate representation. The second possible explanation for why we have a sample statistic that is this high is that maybe it doesn't accurately reflect the population, but maybe it's just because of sampling variability. If it's because of sampling variability, what that means is that the true proportion is not greater than 0.5. Okay, so the claim would be wrong. However, we happen to get, just by random chance, a sample where our proportion was so much higher that it makes it look like the true proportion was greater than 0.5. Okay? These types of samples would not happen very much, but they would happen some, and sometimes by just random chance you get one of these samples that does not reflect the population. So either one of these options, okay, is totally plausible and could happen. So what you have to do is use what we call a significance test to decide which one is the most plausible. Which one is the most likely to happen. Okay, so the basics behind a significance test is that, one, we're going to take a value that we call the null value, and we are going to assume it's true. So we are going to assume the null is true. Okay, if we assume the null is true, then that means we're going to set up our entire problem around it being true. Then we are going to analyze the sampling distribution, assuming that null is true. And we're going to look at the probability of getting a statistic. The statistic that we got when we took our sample. Okay, if the probability of getting that statistic is really small, then we have good evidence that our null probably is incorrect, because we probably should not have gotten that if our null is correct. Okay? Keep in mind, there is always the possibility that we got it just because of random chance and that our null really is correct. So, if the probability is not small or, not very small, then there's nothing that we can say. Okay, it may have happened because of sampling variability. It may have happened because the null is correct. There's not a lot we can say. So the first thing we have to do is to determine our hypotheses. We're going to look at the state, the plan, the do, and the conclude steps for these kind of problems, both for population proportions and population means. And the first part of the state is giving our hypotheses. So the difference between a null and an alternative hypothesis. You must have two. The null here is what we are going to assume is true. Okay? This is what we're basing our whole problem around. So we're going to write it in symbols, h sub 0 of, and then you're going to give some kind of value. So if I'm talking about proportions, it'll be p equals. If I'm talking about means, it'll be mu equals some kind of value. And then I'm looking for a statement of no difference, or the boundary of my problem. So if I look at our original problem up here, I was looking to see if the proportion of couples that kiss the right way is greater than 0.5. So this right here, 0.5, would be my null. Because that's what I'm looking to see if things are greater than, and it's a statement of no difference. If half people kiss the right way and half people kiss to the left way, then 0.5 would be the proportion. So this null would be that p is equal to 0.5. Then we get our alternative. And to get our alternative, we say h sub a. Okay, the alternative is what we're trying to prove. In the problem earlier, we're saying we are trying to find convincing evidence that the proportion is greater than 0.5. Okay, so that would be our null. Your options for your null are either greater than, less than, or not equal to, depending on the situation. Okay, some common mistakes that people make when they state their hypotheses is that, one, they use statistics instead of parameters. We know all the information we need to know about the statistic. There's no use in trying to find proof about a statistic. So what we're trying to find proof about is a claim about a parameter. So you always want to make sure that you use parameters, which means p or mu in your hypotheses. There are actually two different types of hypotheses because we treat hypotheses that are done with less than or greater than different than we treat hypotheses that are done with not equals to. One-sided are ones we do either greater than or less than. Two-sided ones are the not equal to's. Okay, these only apply to the alternative because remember the null always needs to be equal. Okay, the difference is just the direction you're looking. And they both have their ups and downs. Two-sided ones can give us more information because we can really use confidence intervals to get more information if we're using a two-sided hypothesis. But they're kind of harder to prove because I have to split my probability over two ends. One-sided ones, easier to prove, but if I can't prove them, they don't give me as much information as a two-sided hypothesis does. Okay, and we decide by which one to use by looking at the question wording. Okay, look for keywords like more or less or greater than or less than for one-sided ones, and keywords for two-sided hypotheses are things like different or change, where it doesn't specify a direction, it just tells you that it's changing. So let's look at this example. Mike is an avid golfer who wants to improve his play. So a friend suggests getting new clubs and lets Mike try out his 7-iron. Based on years of experience, Mike has established that the mean distance that the ball travels when hit with his old 7-iron is mu equals 175 yards with a standard deviation of sigma equals 15 yards. Okay, remember, these are population parameters because they got Greek letters here. So he is hoping that his new club will make his shots with the 7-iron more consistent. That's important. Okay? And so he goes to the driving range and hits 50 shots with the new 7-iron. So the parameter that we're interested in, because we want to see if it's more consistent, is going to be sigma. Okay? His standard deviation. Because if we are more consistent, that means that the standard deviation of the new club will be smaller. So we're interested in the standard deviation of the new 7-iron. Okay, so our hypotheses. The null is a statement of no difference. If the new club is no different than the old club, then they will have the same standard deviation. So that's where we get our null. We're going to assume that the new club has a standard deviation of 15 yards. What we're wanting to prove, the alternative hypothesis, is that it's more consistent, less variable, which tells us that we would want a standard deviation of less than 15 yards. So there we have our two hypotheses. Okay. P-values go with the conclude step. Okay? Our interpreting them does. So what a p-value is a p-value is the probability of getting the statistic that we observed in our sample. So it is the probability of achieving a certain statistic. Okay, it measures how likely that statistic is to occur. So like our p-hat of 0.669, how likely is it that if our proportion, okay, if our population proportion really is 0.5, how likely is it that we would get something that is 0.669? So when we interpret this value, okay, this is going to have a probability equal to it. There's going to be some number here. And it's going to be a decimal, and it's going to be between 0 and 1 because it is a probability. And so to interpret it, what we say is assuming that the null is true. Okay, the null is this p equals 0.5. So we would say, assuming that it's true, and in context we could say something to the effect of, assuming there is no directional preference there is about a, whatever that number is, percent chance that you would collect a random sample where the proportion is 0.669 or greater. So, we use greater because of our alternative hypothesis. Our alternative hypothesis for the kissing example said we were looking for p to be greater than 0.5. So, that's what bases this or greater off of. Because what we are doing with a p-value is we're saying, what's the probability that we're going to get the statistic that we achieved or something more extreme? Okay, so if this was less than 0.5, we'd be going or less, because we always want more extreme. So you assume the null, and then the p-val tells you what chance you have of collecting a random sample with that proportion or more extreme, or that mean or more extreme, as long as you assume the null is true. So let's look at this final problem. When Mike was testing a new 7-iron, the hypotheses were the null is the standard deviation equals 15, versus the alternative of the standard deviation being less than 15, where sigma is the true standard deviation of the distances Mike hits golf balls using the new 7-iron. Based on 50 shots with the new 7-iron, the standard deviation was 10.9 yards. A significance test using the sample data produced a p-value of 0.002. Okay, so to interpret this in context, we say, assuming that there really was no difference in the standard deviations of the two clubs, okay, so assuming that the standard deviation of the new club really was 15, meaning there was no difference in the standard deviation of the old club and the new club, there is about a 0.2% chance that we would achieve a sample with a standard deviation of 10.9 yards or less. Okay, so remember, assuming the null is true, this is the percent chance, or this is the chance, that you are going to get a sample with that statistic or more extreme. Okay, so does this data provide convincing evidence against the null? And in fact, it does, because this is a really small value. This p-value, the fact that the p-value is so small, tells us that there is only a less than a 1% chance that we would get a statistic like this if this is true. Okay? So since it's less than a 1% chance, I'm going to go out on a limb and say that that's convincing evidence and that that didn't happen by chance. Instead, it happened because this is not true.